let us take up this 2D analysis of pin-jointed plane frames by direct stiffness method. First, let us derive the global stiffness matrix for a pin-jointed frame element. Consider a 2D pin-jointed plane frame element 1, 2. So always each element that should be named by two ends, 1 and 2, end 1 and end 2. The element coordinates, as I told you, always the axis of the element is chosen as the origin. Now, axis of the element is chosen as one of the axes, and the other two normal to it are chosen as the other two coordinate axes. So this is xn member axis, this is y-axis, and of course z is normal to this. And global coordinates are this always horizontal axis is chosen as global x-axis, other two normal to it are chosen as the other two coordinate axes. So I am considering a 2D jointed plane frame element 1, 2 in local and global axis. This is with respect to local axis, this is with respect to global axis. Let L be the length of the element, EA is the axial rigidity, and small l and small m are the direction cosines. Let L be the length of element, and small l and m be the direction cosines dc of element, and AE is the axial rigidity of element, which I have indicated. So the displacements in local and global axis are this. So let d1 be the axial displacement, d2 be the axial displacement at 2. Let d1 and d2 be the displacements in local coordinates. Displacements in local coordinates along at 1 and 2. The corresponding the displacements, let the corresponding displacement in global coordinates, let corresponding displacements in global coordinates at 1 and 2 be u1, v1 and u2, v2 as in figure. With respect to global coordinates, the displacement at 1, let it be u1, displacement along y, it is v1. Similarly, at 2, displacement with respect to global axis is u2 and v2. So this is the displacements in member 1, 2 with respect to global and local axis. With respect to local axis, d1, d2 are the displacements. With respect to global axis, u1, v1 are the displacements. So along the local axis, there will be only one displacement in one node, that is either d1 or d2, whereas global displacements are two, because stress is always subjected to only one axial force, and corresponding to that, only one axial displacement. But if you take global, this particular axial displacement will give rise to two components along the global direction. So you have to represent the two displacements. That is why it is called as 2D pinjointed plate. Though the along the member axis there is only one displacement and one force to be determined during analysis, but when we talk about global coordinates, so there will be two forces corresponding to two displacements. Similarly, if you represent the forces, so the forces, if you take displacements and forces, both if you take. So if you take display forces, then there will be a force here, that is P, axial force at 2, then axial force here, this global force, this local forces, here if you call it as P, here it will be equal and opposite for an equilibrium. P, P, they are the forces, and the corresponding forces in the global direction is here, you call this as Px1, this as Py1, this as Px2, this as Py2. So this is node 1, node 2, node 1, node 2. So displacements and forces. These are the forces. So in the local axis, there is only one force, one axial force in the member 1, 2, and that axial force we either maybe compression or tension. Usually we take tension as the positive direction. So this is the element I am considering, the 2D pin jointed frame element. Now let us derive the global stiffness matrix for this element. So we have, so we can say let the corresponding forces with respect to local and global coordinates, with respect to local and global coordinates, or P and Px1, Py1, Px2, Py2 as in figure. So again, global axis, there will be four forces. In local axis, there is only one force, because this will be in equilibrium. These P should be equal to this equivalent opposite that already I have told. There will be only one independent force in the stress element. Now, we have this. First, let us take the displacements. We have this U1 is nothing but, or D1. If you take D1 is nothing but U1 L plus E1 M. So this displacement you can resolve with respect to U1 and E1. U1 if you resolve along the axis, that will be U1 cos theta. U1 cos theta is nothing but L, U1 L. Similarly, V1 into sin theta, that is V1 m. So these components U1 and V1 along the axis of the element, that is the displacement, net displacement with respect to global coordinates. The displacement, result component of the displacements with respect to global coordinates along the axis of the member, that is U1L plus V1M, and that should be equal to the local displacement D1. On similar lines, you can say D2 is also equal to U2L plus V2M. This is U2L cos theta, V2M sin theta, that is nothing but U2L and V2M. Therefore, net displacement delta is nothing but this difference in the displacements along the axial direction, that is D2 minus D1. Therefore, strain in the element epsilon is equal to delta by L, that is equal to D2 minus D1 divided by L. And stress is equal to sigma, that is V epsilon, that is nothing but E delta by L. E delta by L or E D2 minus D1 by L. Therefore, the axial force in the element, that is nothing but P. The axial force in the element is nothing but P, that is equal to sigma into A. Stress into area of cross section, that's the axial force, or that is nothing but E A by L into delta. E delta by L is the strain, axial stress, multiplied by A, or I can write it as A by L into delta. That is your axial force, A by L into delta. That is that force of the element. Now, this delta is this D2 minus D1 A by L into D2 minus D1. Or this P, you can write it A by L D2 minus D1. So D1 is given by U1 L plus V1M. D2 is given by U2L plus V2M. If you substitute that, this A by L into this is U2L plus U1L plus V1M. This is U2L plus V2M, that is D2 minus U1L minus V1M, that is your D1. Or this you can write it as A by L into U, and write as minus of U1 minus or U2 minus U1 into L plus V2 minus V1 into M. This is that P. P is given by that axial force is given by that. So the axial force at 2, it is plus P. Axial force at 1, it is opposite, minus P. So, and also you can say also B1 is that, also you have this Px1 is nothing but minus P into L from this. This Px1 cos theta is nothing but minus E, or that is Px cos P minus Pl is Px1 and Py1 is equal to minus Pm, it's what you got, minus Pm, and Px2 is equal to Pl and Py2 is Pm. Therefore, Px1 is equal to P, I can substitute this A by L into P is this A by L into U2 minus U1 into L plus U2 minus V1 into M into L. This for P I am substituting from here A by L U2 minus U1 into L plus V2 minus V1 into M, that into L. Or this you can write it as UA by L. Okay, let it be there as C. Similarly, Py1 is A by L on similar lines. Py1 is minus Pm. P is nothing but this, that is A by L U2 minus U1, okay, that is minus P, minus P, that is minus A by L into this. Similarly, Py1 is minus A by L into this, L plus U2 minus U1 into M into M. P is this into M. And Px2 is equal to P, that is plus A by L into E is U2 minus U1 L plus U2 minus V1 into M into L. And Py2 equals A by L into U2 minus U1 into L plus U2 minus V1 into M into M. So I have the forces. First, I derive express the displacements in local coordinates with respect to global coordinates, and then I express the force corresponding to local coordinates. Then I expressed global forces in terms of these local forces. I got this. So therefore, now you can say this, hence the above equations, that is these four equations, hence the above equations can be written in matrix form as, I will write this Px1, Py1, Px2, Py2. These are the forces in global coordinates, Px1, Py1, Px2, Py2 in global coordinates, that is equal to this Ea by L into these displacements U1, V1, U2, V2. The global forces Px1, Py1, Px2, Py2, that is related to global displacements U1, V1, U2, V2, that is from this. So you know that Px1 is A by L into, here now if you simplify, it is minus into minus here. It is u2 minus u1. So minus minus it becomes plus. So that is this u1 plus u1 L into L, that becomes L square. L into L square, this minus minus plus, plus u1 L square. And V1 is again minus minus plus, it is M. So M, this is V1, it is minus minus plus, so it is M. For V1, it is L into M into minus V1 into minus plus V1. Then U2, it is L, U2L, it minus U2L into L square, that is U2 minus L square. Then V2ML minus V2LM, that is that. So this is U1L square, that is plus U1L square plus V1LM minus U2L square minus V2LM, that is from this automatically you will get it. Like that, V1 is LM U1, this is M square U2, then V1 means it is M square, then V1 over U2 is this U2LM minus LM into U2, and V2 is minus M square. LM U1, LM U1, of course it is plus, minus. Then with respect to V1, that is minus V1 M square, of course minus plus, so it is V1 M square. Then U2 minus U2 LM and U2 M square. Similarly, Px2 is given by A by L into U1. U1 is minus L into L minus L square. Then with respect to V1, it is minus LM, and U2, it is L square, and V2, it is LM. Then lastly, Py2 is minus U1 LM, that is minus LM, then U2 LM, U2 V1 minus V1 M square, then U2 LM, then V2 M square. So this is the formula. So this particular equation, I have cut this entire 4 equations, I wrote it in matrix form like that. So this is nothing but our force is equal to, this is nothing but the displacement both in global coordinates. Force in global coordinates, displacements in global coordinates, that is related in this fashion, and that relation is nothing but my element stiffness matrix. So this is your global stiffness matrix, where AS is global stiffness matrix directly with respect to global axis. Global stiffness matrix of a 2D thin jointed element. So that is nothing but A by L into this L squared Lm minus L squared Lm. It's a 4 by 4 matrix. 4 by 4. So that you have to memorize. I have derived. So this is directly the stiffness matrix in global coordinates. Loads everything will be in the global direction. Straight away I can use this force displacement relationship the moment I generated this stiffness matrix. After all, you know here the stiffness matrix is a function of E, A, L and which direction cosines Lm. They are all known quantities. EA, L, direction cosines Lm, they are all known quantities of a given element. The moment element is given, you know its length, you know its EA value, you know its direction cosines. So thereby, straight away, you can generate the corresponding global stiffness matrix straight away for all the elements. You can write this stiffness matrix with respect to global coordinates mainly from the geometrical property point of view. Then you can add, you will get the total structure stiffness matrix. Then you can use this relationship. Load is equal to PS cos Ks into ds. So load is also in the global coordinates. It is known. Load is known. Stiffness matrix is known. So displacement you can easily compute at various joints, either by solving this equation or by inverting the stiffness matrix, then multiplying by the load. That's all. The procedure is very simple. That's why it is called as direct stiffness method. Here we are generating the stiffness matrix directly in global coordinates. Straight away now we can use it. Hitherto in the other two methods, whatever you have done, you were doing the calculations. Here, already I have derived the stiffness matrix for a general conjoined frame. Directly you can use it. Only you have to determine those geometrical properties correctly and then use simple force displacement relationship to compute the displacement. The moment you know the displacement, that is ds, that is U1, U2, V1, V2, they are all known. ds is nothing but U1, V1, U2, V2, they are all known. When once they are all known, the force in the element P is the force in the element. The force in the element straight away you can determine. That's all the analysis. Analysis becomes very, very simple. Only you have to generate the element stiffness matrix in global coordinates. Then you have to determine the global stiffness matrix of the entire structure. Then use simple force displacement relationship, evaluate the displacement. Then use this relationship to compute the element forces. That's all the analysis of this 2D conjoined truss, the general procedure. So you have to memorize or you have to remember this stiffness matrix of a truss plane truss element. That is A by L squared Ln minus L squared minus Ln. Then m square minus Lm minus m square L square Lm, then m square. Only you can remember the elements above that in diagonal. Others are all symmetric below the diagonal. It is always a symmetrical member. You can remember easily without any problem. Then use that straight away in working problems on all conjoined plane. That is all plane trusses. So this is about analysis of conjoined frame. Only first preliminary, I have already told you, you have to find joint information, member information, degrees of freedom, as I have told. Joint information means the coordinate of these axes to compute your direction, cosines and length. You have to do this information, joint information, then member information, its area of cross section, L and all. Then EA by L you have to compute for all the things. Then doing all that preliminary data collection, you can compute stiffness matrix by remembering this formula straight away for all the elements then compute for the entire structure by combining for all the elements. Then for the entire structure, you can write this force displacement relationship. Loads are also known at all the nodal points. It will given this generated source, this displacement, you can easily determine. After determining displacement, that is these global displacements, you can compute the element member forces. That's how the general procedure. That we will work problems into that. Now, only the theory behind this direct stiffness method of this analysis of forces is only this. So that is how to derive the global stiffness matrix and how to derive the member forces. That also to remember. And also you can just write that rotation matrix or displacement transformation matrix also you can remember. Either you can derive this global stiffness matrix straight away from this, or by deriving that displacement transformation matrix and applying that principle of contragradient, also you can do it. So that I will show you here. So that is a very simple exercise. Or we can derive that same global stiffness matrix like that. So we have D1 is equal to this U1L plus U1M, and D2 is U2L plus U2M. That's the relationship between global displacement and local displacement. That have to simple resolutions. So, or we can write this global displacement or local displacement in matrix form like this. M into this U1, V1, U2, V. This equation, you can write it in this fashion. You see, D1 equals M into U1, M into V1, 0 U2, 0 V2. That's first equation. Similarly, D2 is nothing but 0 U1, 0 V1, L U2, M V2. This equation you are writing in general form. That means this is your local displacement. This is that matrix relating this local displacement with global displacement. This is global displacement. It is related to local displacement by this matrix. This we call it as the displacement transformation matrix, which I defined earlier. Transformation matrix for this 2D element. The moment you know this, then this global stiffness matrix is given by RT into Km into R. That standard formula, you know that by principle of contragradient, by principle of contragradient. So this R can use it, RT you have to write, and this Km, element stiffness matrix of a truss, that it is given by AE by L minus 1. That also we know. Use that RT, Km, or that if you simplify, you will get this A by L, L squared by L, same thing you will get it. So either you can derive the global stiffness matrix from this fundamentals of principle of contragradient, you can derive it in this fashion or in this fashion, just by taking each element in local global coordinate by resolving that also. Okay. Either way, you can just do it. And anyway, all leads to same thing. Only you have to remember that straight away the global stiffness matrix of a truss element. That is EA by L, that 4 by 4 matrix. L squared L minus is what you have to memorize, and you can work any problem straight away. Of course, force displacement relationship you remember. And for finally computing member forces, you can use this one. That's all the procedure in direct stiffness method. Now we will take up that in similar way 2D analysis of a rigid jointed frame of rigid jointed frames by direct stiffness method. So this procedure applies for truss analysis or truss. This which I am going to now derive, that is applicable for beams and rigid plane frame, both rectangular rigid frames as well as inclined leg also. So that also I can do it. Whereas earlier methods, inclined leg, you were not doing, whereas here direct stiffness method, straight away you can apply for inclined leg also. So as usual, you consider a 2D rigid jointed plane frame element in local and global axis as in figure. I will show you a figure, similar figure. It can be in any direction in the plane. In the plane, it should be a plane frame. In the plane, you can consider that element. The element 1, 2, of course, in local coordinates. So this is the displacement. Here there will be 3 displacements in local as well as global coordinates. So this is axial displacement UA2, UA1, axial displacement at node 1. This is vertical displacement, normal displacement at node 1, normal displacement at node 2, and of course rotation. This rotation is about this z-axis, which is common for local as well as global coordinates. That's the advantage. So I will call this as θ1. Here rotation. It is about same axis, that I will call it as θ2. We don't say whether it is axis or normal. It is always normal, about the normal to the board, normal to the plane in which this member lies. That is z-axis is always normal. So this is nothing but displacements in local coordinates. Then corresponding displacements in global coordinates. Of course, length of the member, you can take it as L. Here is the flexural rigidity L and M, and direction cosines. The direction cosines also required because I am taking member in any direction in the given plane. Earlier, I was taking either horizontal or vertical, truly orthogonal, vertical leg. Now, I am taking any member in the plane. Of course, it is a plane free member in any direction in the plane. Of course, not outside the plane. So that's the only thing. So here again, same member in global coordinates, displacements like this with respect to global axis. Here I will call this as U1, V1, U2, V2, and of course rotation about z-axis. The z-axis for this global axis is also same. There is no change. Even for member local axis also, z-axis is same. Here also it is same. So these displacements I can take it as same, theta 1, theta 2, there is no tail. It is about the same axis. That is displacement in local coordinates and global coordinates. Both I have marked here. This is local coordinates, this is with respect to global coordinates. All displacements I have marked. Similarly, the forces I will mark it in different picture because it is a rigid plane frame member, either a beam or a rigid plane frame member. Here the forces, here it is axial force. I will call this axial force as P1, this as P2 at node 1, node 2, and this is shear force. I will call it as Q2. Here shear force, I can call it as Q1, and of course here moment, I will call this as M1. Here moment, I will call M2. These are the forces at the ends of the members in local coordinates. Local coordinate means the axis of the member is what? X-axis, and other normal to the other two coordinates. Similarly, the forces in global coordinates of same member 1, 2. In global coordinates, the force here I will call it as Px1. Here I will call it as Py1. That is force along x direction at node 1, force along y direction at node 1, and moment at 1. Of course, the z-axis is same. I will use the same notation, M1, I can use it. Because for local axis as well as global axis, z-axis is same, I can use same notation. Here at node 2, along the x direction, I will call it as Px2. Along y direction, I will call it as Py2 at node 2, and moment M2, because it is same as this. So these are the forces in local and global axes, global coordinate axis. These are all displacements, these are all the corresponding forces. So you consider a 2D rigid jointed plane frame element 1, 2 in local and global axis as in this figure, that L1 is this direction cosines and EI is flexural rigidity. It's a flexural member. So I am taking flexural member subjected to axial force also. Flexure as well as axial. If the member is axially rigid, then you can take UA1 as 0. That's all. It's only shear and flexure. So here is the flexural rigidity. In local and global coordinate directions, I have just told you. Now, as usual, you find the relationship between local and global displacements. So we can write it, this U1 is nothing but, or we say UA1 is nothing but U1 L. UA1 is nothing but U1L plus V1M. This UA1, this U1 if you resolve, this is theta. So U1 if you resolve like that, U1L, U1 cos theta. U1 cos theta is nothing but U1 into L, that is UA1. Similarly, this V1 if you resolve, this is theta of the time, this is sin of 90 minus theta, this is 90 minus theta, so this component is cos of 90 minus theta, that is sin theta. Therefore, this force will be V1 into sin theta, that is V1M. So U1L plus V1M is nothing but your UA1. That's the relationship between axial displacement and the global displacement. On similar lines, UA2, you can write it as, say, U2L plus V2M. U2L plus V2M. You can write it similar to this. Then UN1 is VN1, that is this normal displacement. V1N is nothing but minus U1M plus V1L. This, if you resolve this component, it is like this. V1 direction is like this. En1 direction. That's why I am attaching a negative sign. So this will be U1 sin theta, that is U1M. It is in the opposite direction. Whereas this V1 we can resolve like that itself, that is positive V1. This sin of 90 minus theta, that is cos theta, V1 cos theta, that is V1, yeah, that is positive. On same lines, this Vn2 is minus V2m plus V2m. One if you write, other automatically you can write. And this displacement theta1 is theta1 in local and global, they are same. In local, global, they are same. Therefore, now we can relate this UA1, VN1, theta1 is displacements at node 1 in local coordinates that we can relate to global. UA2, VN2, theta2 at node 2, these we can relate to these global displacements, that is U1, V1, theta1, U2, V2, theta2. From this, I have written here by just simple resolutions resolving this displacement. Displacement is also vector, similar to force. I can resolve the displacements I got like this after resolving these displacements. So I will take this, you can write it in matrix form in this fashion. UA1 is U1L plus V1M and others are all 0. U1L, V1M, 0 theta1, 0 U2, 0 V2, 0 theta2, that is UA1. Similarly, VN1 is minus MU1 and V1L and the rest are all 0. Then theta1 is theta1 itself, that is 0, 0, 1. Theta1, others are all 0. Theta1 equals theta1. On same as this UA2, this is 0, then M, 0, UA2 is 0 U1, 0 V1, 0 theta1, U2N, V2 M, then 0 theta2, that is this UA2. Similarly, V12, you can write it in matrix form. This is minus M, L, then theta2. That is 1. Theta2 equals theta2. This is that writing. This displacement, whatever I have resolved and got it, I am writing in matrix form. So therefore, this is your local displacement, dm, member displacement. It is related to this global displacement by a matrix which we call it as the displacement transformation matrix. This is nothing but displacement transformation matrix. Transformation matrix. Straight away, get it. The second method I am using now for this 2D frame element to write the global stiffness matrix. So then once I know this rotation matrix, I can use the principle of contra gradient by principle of contra gradients. This Ks global stiffness matrix of this 2D rigid frame element is given by this RT Km R. Where this Km is nothing but the stiffness matrix in element coordinates, which already I had derived. It is element stiffness matrix, which is nothing but element stiffness matrix. This is with respect to these coordinates UA1, VN1, theta1, with respect to that, that is given by A by L 0, 0. It is a 6 by 6 matrix because 3 here, 3 here, 6. So it is a 6 by 6 matrix, whereas in truss it is just 2 by 2. Only one force, P, P1, P2, axial force. So it is a 2 by 2 matrix, that is A by L 1 minus 1 minus 1 1. Here it is a 3 by 6 by 6 matrix with respect to axial, vertical as well as rotation. So it is like this. A by L, which already I have derived in the very first or second lecture or so. Then I have where this is minus A by L, minus A by L, minus A by L, and this is where EI by L cube, then LVI by L cube if I give it, then this is minus 12 EI by L cube. This is like this, it gives a opposite direction, so this will be 6 EI by L square. This is minus 6 EI by L square. So this has to be symmetric, that is minus 6 EI by L square, 0 minus L EI by L cube. This is 6 EI by L square. This is that stiffness matrix with respect to second coordinate. Then I have here 4 EI by L and 0, 4 EI by L like this, here like this. So this is 6 EI by L square, 6 EI by L square, 2 EI by L. And 0, 6 EI by L square, and 2 EI by L. This you have to remember. That then I have here EA by L 0, 0, 0, 0 by L. Then I have 12 EA by L cube and 6 EA by L square. That is 10 EA by L cube. This opposite, that is it opposite. what's known as 6a by L square. This is 6a by L square. This is the element stiffness matrix, which you have to remember. Or this I will use a single notation. You can remember this E A by L, I can call it as S, then this will be 0, 0, minus S, 0, 0. I will call this 12A by L cube as B. Then this as C, 0, minus P, minus C, and this is 0, minus S, 0. This is easier. Instead of 12A by L cube, 6A by L square, you can use this notation straight away. This minus C, 0, minus B, minus C. This 4A by L, that is D, you can call it. This is 0, this is C, this is D by 2. 0, C, D by 2. And this is A by L, yes, 0, 0, 0, 0. That is 12A by L cube B. This is 6A by L squared C, C, D. So you can remember this number stiffness matrix in this fashion. Where this S is nothing but A by L and B is nothing but 12 A by L cube. C is 6 A by L square and D is 4 A by L. When doing determining the member properties preliminarily, we can evaluate this as B, C, D also, because everything is given, known in the problem. So first you compute this S, B, C, D, and all, knowing its A value, length, everything, so that straight away you can write this K. Then you can just use that formula. Therefore, this Kf is nothing but this RT, Km, or you can just use it. If you multiply this straight away, you will get the big matrix, that is Kf is given by, I will write that. That of course you have to remember. So that is given by, this is B M square plus S L square. M square plus SL square, then minus of B minus S into Ln. Of course, I need more space. I will use there, I think it is better. Because it's a big matrix. It's a matter that we try to write it. Bm square, I'll try to match that. Bm square plus SL square. It's a 6 by 6 matrix which you have to remember. Like stress. Stress is no problem, but this is a bigger matrix, so you have to remember it. There's no other no. So that is Bm square plus SL square minus of B minus S into Ln, then Cm, then minus Bm square plus SL square, Bm square plus SL square, then B minus S, Ln, minus S, Ln, then Cm. That is the first. So this is similar, B minus S ln Cm, then Bm square minus, of course, minus Bm square plus Sl square, then B minus S ln and Cm. So then the second element, it is B L square Sm square. Here it is Bm square Sm square, here Bl square Sm square. Then minus Cl, then B minus S ln, then minus Bl square Sm square, and minus Cl. So it is similar, Cl minus B minus S ln, then this is minus Bl square Sm square M square, then minus Cl. That is that second row. Then this is one element B, then this is minus Cm, Cl, this is D by 2, that is 2Ei by L. So then here it is minus Cm, Cl, D by 2, because it is symmetric. Then this is same as this, Bm square plus Sl square. Bm square plus Sl square, this is minus of B minus S ln, then minus Cm, minus of B minus S ln minus Cm, then here it is B, this one, Bl square plus Sm square, and this is Cl, this also Cl, then this is D. We see that after simplification or transpose into Km is this, into again R. If you simplify this, you will get this matrix. So this is the global stiffness matrix of a 2D rigid frame. That is both beam as well as rigid plane frame. That is the global stiffness matrix. That you can see, they are all in terms of known quantities. That B, S, D, C, they are all in terms of known quantities. That is EA, EI, L, they are all known properties of the member. We can generate that stiffness matrix. Again, when once you know this for each member, similar to stress is L squared lambda, that's 4 by 4 matrix. Here it's a 6 by 6 matrix in global coordinates. Straight away you can remember. That's why it is called as direct stiffness method. Stiffness matrix will be directly given in global coordinates. What you have to do is, for each element, knowing their element properties, you can generate the global stiffness matrix. Then you can use this relationship. Ps is equal to Ks, ds, and you can compute ds from that. Either by solving that equation or by inversion of that stiffness matrix, we can determine the unknown displacement. Because Ps is also is given in the problem, equivalent joint loads. So use that, we can find out the displacement. Then we can determine the member end forces. So straight away, after converting the ds to dm and then knowing km and dm, we can find out the element member forces. Or you can use straight away slope deflection equations, so which gives moment, which relates moment in terms of displacements at the end, slope as well as that relative translations V1 and V2 at the ends. So knowing that slope deflection equation, we can calculate the member end forces. That's the analysis procedure. So now I have given the procedure for analysis of a 2D pin jointed frame, that is stress problems, and 2D rigid jointed frames, that is beam and plane frame problem. So you have to memorize this stiffness matrix. Here for 2D rigid frames, there 2D plane truss. Remembering that, as well as of course this also you can remember, they are simple. K member stiffness matrix and rotation matrix. Using that force displacement relationship, you can just complete the analysis without any further complicated analysis. Then you will be giving unit displacements, unit forces, one at a time, all those things. Those things are not there directly. You have to remember these stiffness matrices. That is called as direct stiffness method of analysis. The final formula, whatever I derived here, a typical 2D rigid joint frames, that is both for beams and this. If it is axially rigid, automatically this S will be 0. And it is axially rigid, so they will not give the area of cross section. It will not be used straight away. S will be 0 in all these. And also, if it is perfectly horizontal beam problem, all members are all lying in only horizontal plane, for which direction cosine with respect to y-axis m, small m, that will be 0. So m, small m will be 0, only n, small n will be 1, because it is cosine 0, that will be 1. S also will be 0, automatically things will get simplified. So it will come to only this much for beam problem, which is not which is axially rigid. If it is not axially rigid, then that big formula you have to remember. Both axially rigid as well as inclined leg, all problems you can solve. That is why this method is most widely used method, direct stiffness method for that. So this straight away you can program it on a computer easily. Only that stiffness matrix straight away you can feed it to the computer, and before that, the coordinate information and joint information, member information and restraint conditions, all those preliminary data you feed it, straight away it will compute that stiffness matrix. Formula you can give it, that 6x6 matrix, straight away you can ask it to read for all the elements, element 1 to 100, you can get a tree, assemble it, then just solve it finally. PS also will be known, solve it, you will get displacements, straight away that you will get as output, and element properties straight away again, you can use that relationship PM, AM, DM, from that you can come to member end forces. So complete analysis can be done just by remembering this global stiffness matrix as well as element stiffness matrix, that is your slope deflection equations, which relates the member end forces with the displacements. That is the two slope deflection equation. So feeding that slope deflection equations into the computer, straight away you can compute. That's again in terms of these things only, BCD, 4 year by year, 2 year by year and all. So this, I have given the general procedure for analysis of both beams, frames, trusses. Next class onwards I will take up straight away one problem, maybe on the 1 or 2 classes. One class I can work one of typical beam stress problem, another plane strain problem. I will show you the procedure. Only theory behind it is only this: how to derive global stiffness matrix for a typical 2D rigid jointed frame, 2D pin jointed frame. That I have given you. That you have to memorize along with this member stiffness matrix as well as this. These three formulas for each. For 2D rigid frame, this final global stiffness matrix, element stiffness matrix, and displacement transformation matrix. Likewise, for pressures, that global L square element of the global stiffness matrix, EA by L 1 minus 1 minus 1 1 element stiffness matrix, potential matrix A L M 0 0 0 0 L. That's only 2 by 2. Here they are all 6 by 6. So with this, yeah, and of course, grid problems, it is just similar to this plane frame problems. Plane frame, they are all in vertical frame. If you transfer, rotate it through 90 degree, it will be a horizontal plane. Same type of analysis you can do for grids. Grids, vertical plane, horizontal plane, vertical plane, then 3D analysis also can do on similar lines. Of course, it is not very cerebral. 3D analysis and grids, only these. It is just, it is all 3D.